Okay, so I'll start. So I'm here as a representative of the core facility of the Alsace node, and Yves is our node head, and he will focus more on the R&D team that we have in actions in the Alsace node. So just to remind you where we are, we're just at the border with Germany, at the other side of France, really at the edge of France. And so the node regroups 7 large institutes that are really focused from studying life from molecule to small animals and plants. I mean, like anywhere else, I guess. We are 6 life science imaging facility localized in Strasbourg, and then suburbs of Strasbourg, 5 kilometers away from the city center, Illkirch, and then 100 kilometers down the south of Alsace, Mulhouse. And with our facility, we go through 6 R&D team, and our focus is really in new probes development, and then strengthened by optical instrument and software developments. And Yves will develop more on that aspect. So I'll pass that out. So just to put a face on who's who. So we got 6 R&D team, Loïc Charbonnière, Andrei Klimchenko, and Yves Melly, really working on probe and chemistry of light. The team of Yves is also in the interface with probes and development of instrumentations. Olivier Berlet works on instrumentations as well as the team of Sylvain Leclerc. And then the last team is the team of Bruno Klaus that works on both instrumentations and software development. And for my part, I'm part of the group of people that build up all the consortiums of the facilities in Alsace, and then also part of the France-BioImaging node. So Jean-Daniel, Sylvette, and Pierre, sorry, Pierre, no picture there, Pascal Kessler and Jérôme that are the city center of Strasbourg, myself and Ludovic in Illkirch, and then we have also Tatiana in Mulhouse. And I'll focus more on who's doing what. But as you can say, each facility has a focus on the topic of research of their own institute. So ranging from inflammation and immunology, neuroscience imaging, in vivo imaging, plant imaging for Jérôme and Ludovic and I on more on live and molecular and cell imaging, and Tatiana on biomaterials. So where are we localized? So we are not as regrouped as Toulouse, but really across the whole of Alsace, both Alsace departments. So Strasbourg and Illkirch is 5 kilometers, so it's like 30 minutes by public transport, and Mulhouse by train is 1 hour from the main site in Strasbourg. And so we are geographically separated, but by time it's not much big deal. And now with Zoom, it's even easier. So what do we do? In terms of the core facility, we do like anyone else does now in France. We do multiple imaging from single molecule imaging, so super resolution microscopy, to large sample with light sheet microscopy. And because we're doing biology, a lot of live samples. So in terms of staffing, we are less people than here, less instruments. So 19 full-time equivalent staff, 47 instruments available. So of course, less machine hours, 45,000 in 2021, I think it was. A bit less than 400 users. And what do? We train more or less 145 users per year. We do a lot of training in terms of image analysis and processing. So we got 100 attendees every year. And of course, we carry on doing workshop on our new technology that we acquire, so the STED, the light sheet, and so on. And we are involved, as many of us, of you have seen us in Mifobio with the RTMFM and the GDR, and so on and so on. So, and then, of course, just a summary of what we do. We take our users from the research project, the experimental design, of course, the imaging, and also the image analysis, and ranging from the whole organisms to the molecule. So before letting the chair to Yves, so in summary, you have the core facility, and then you got all the innovative R&D that we have, and in Alsace we really focus on the probe and chemistry of light with 3 teams that are also then 3 teams that work on advanced microscopy, and 1 team on software image analysis. And that corresponds to 38 full-time staff with 90 publications a year, 17 patents currently, 1 startup, and Yves will give you more detail about that.
Thank you for introducing the first part. So I am in charge of the research and development team. So the first team is the one from Andrei Klimchenko you probably heard about. He is a guy who is developing a number of very innovative molecular or nanoparticular fluorescent probes. So first of all, on the level of the molecular probes, so it's mainly probes for labeling biomembranes, organelles. Also, he developed a number of RNA aptamers to recognize selectively some sequences inside the cell, and also some ligands which recognize membrane receptors. So now he is more focused on bright fluorescence nanoparticle, which I had made off of a matrix, which is generally polymer. And inside you have a large number of dyes inside, fluorophores, classical fluorophores, and they are prevented to interact with each other because they have these anions, which are very big. So with these tools, he developed nanoantennas for RNA DNA detection, and this was at the basis of this startup. And he has also tools for biosensing and bioimaging, for instance here cell barcoding and tracking, and here small animal imaging. So the second tool is the team of Loïc Charbonnière. He is a specialist of up-converting luminescent probes. So you probably heard about UCNPs, up-converting nanoparticles. They have the particularity to be illuminated in the infrared and to emit in the visible, which is in the other direction of the classical fluorescent probes. And this, of course, gives a very good signal-to-noise ratio. And so he developed a number of UCNPs, which he functionalized later on. So he has also this kind of application with lanthanide-loaded polymers. And the idea is to do time-gated cell imaging because the lifetime of this object is very high. So the most fancy development is the molecular conversion, which is super difficult to do because lanthanides are not so bright. So to imagine to do the lanthanides with some molecular stuff, just the molecular core, it is quite challenging. And he succeeded to do a few generations of them, which are of course not super bright in water, but they start emitting in water. And so there is a good hope that in the future we can gain a bit in brightness in this area. The next one I know a little bit more. It's my own team. We are developing instruments, but generally it's based on some fluorescent probe, and we want to have some instruments which are specifically designed. So we have been developing spectral paint. So spectral paint is you have the superlocalization method on one side, which is here, and at the same time you record the spectra. And this was based on our Nile red probe. We have generation of Nile red probes that we have been designing. And this Nile red probe are super sensitive to the environment, which makes sense then to record at the same time that you record their positions, that you record their spectra. So we have more recently developed this DREAD paint, which is another variant of paint, where DREAD stands for dark resonance energy transfer. The idea is to have one of the imager strand being almost not fluorescent when it is in solution, and when it comes in contact to the other strand, which is fixed to an antibody, for instance, you have the resonance energy transfer, and then you can do this kind of imaging. So this is a classical turf image, and this is the one that you obtain with the DREAD paint. So we have been developing some time ago already this two-photon microscopy, which is doing FLIM and FCS. And it was very interesting for these 3-hydroxychromone dyes, which are also environment sensitive, which are binding inside the membrane. And for instance, they are super sensitive to the lipid order. You can distinguish between ordered domains and disordered domains. So you can do that either by ratiometric imaging, so you check the color at the two edges here, and you make the ratio of them, and you can distinguish lipid disordered and lipid ordered phase, and even more easier in film, you can really see a big difference between an intact cell and a cell which has been depleted by cholesterol. The same applies if you go for apoptotic cells. So the next team is the team of Sylvain Leclerc. They are more recent in the field, and they start to develop advanced microscopy technique. And for instance, here you have this multi-well plate imager, which is based on halo illumination, and there is a light sheet imaging with single objective near the sample. And this is the kind of image they have been recording on tumor spheroid. Next team is the one of Bruno Klaus. He's doing some instrumentation, but his main efforts are in developing softwares. You probably heard about these softwares, which are SharpVisu, ClusterVisu, and SharpVisu 3D. So the idea is to apply them for SMLM data and to get as much as possible out of them. So the last team is the one of Olivier Eberle, who is developing high-resolution 3D tomographic diffractive microscopy, so the one that does not need to label samples, which is cool in a certain application. And they have been working since quite a long time already on this field, and they have done the first proof of concept experiments, and they did even the world first refraction fluorescent 3D imaging in biological sample. So the lateral resolution is 130 nanometer, which is not bad. And now they are working a lot on isotropic resolution and 3D real-time TDM. And these are the kind of images they have been getting on this, using this kind of techniques. So we are not organized since as long as in Toulouse, but we have already started several years back to exchange and to transfer the technology. For instance, this is an example where Olivier Eberle, I was just talking about, was transferring an instrument to the platform in IGBMC. So the transfer of technology was based on differential spinning disk confocal tomography setup. So they have been adding the tomography setup on the spinning disk. And now they are going on adding this polarized tomography on a confocal head, and in order to get this kind of imaging. Another application where there have been a connection between research and development team and the Quest platform, which is the one also at the Ilkirch place. And the dyes in this case are optimized fluorescent nucleoside analogs, which we are working on this kind of object. So they are perfect analogs of guanine, so they substitute perfectly, but they stay fluorescent even when they are nucleic acid, which is quite unique. And so they are even environment sensitive. So they are very practical. We have extensively characterized their photophysics. And we have been developing, based on that, two instruments. One, it's a single molecule level instrument. And this one is one which are starting to develop, which is at the cellular level, in order to follow in real time this fluorophores when they are inserted in nucleic acid inside the cell. So I will talk about this tomorrow in the tech transfer session. So we have been also developing an anti-stoke microscope for monitoring UCNPs and up-converting supramolecular assemblies. So again, it's in connection with this platform. So all these instruments that I am talking about are on the platform and are fully accessible from anybody. So the idea was to use the object developed by Loïc Charbonnière for the molecular assemblies and Thomas Hirsch for the classical UCNP, but he is doing very advanced one. And so we have been developing two setups, one which is in the confocal mode, one which is in the wide field mode. And for instance, these are single UCNPs, which are followed by in time. And one of the nicest applications was this one, because you know that they do not blink. They are fully photostable. You can image them for hours, and that's why you can have long SPT traces without any photo bleaching. You can follow as long as you can, at least as long as it stays in the field. There are also, of course, development of probes which are used for in vivo imaging. So this is a collaboration of the probe developed by Andrei and the CRBS platform, which is in vivo imaging. So, for instance, here you have these nanoparticles which are tracked in vivo. You see at different times that they accumulate in certain organs. Here you have extracellular vesicles that can be tracked as well using this kind of probes. Tumor targeting in vivo has been done as well. As you can see here, it's very clear where they accumulate. And even in the zebrafish, they have been barcoding and in vivo tracking, which has been done. So to show that we are not keeping everything in Strasbourg, but we are also going to other FBI core facilities. So for instance, this is this NEURIMAGE in Paris core facility, which have been using this LipiBright and MemBright dyes. So they are commercially available now. And they have done a number of imaging, especially in neurons, with this kind of objects. So to summarize, the Alsace node is characterized by original innovation in molecular nanoparticular probe, supported by dedicated imaging techniques and also data analysis. So 6 core facilities hosted in large institutes, which are visible at the international level, specialized in a wide range of biological research. It goes from the plant to the neurons to the cancer and so on. We have also, as in Toulouse, a close collaboration with other national infrastructure nodes. And the peculiarity, of course, of Strasbourg, it's not very far from Germany. And we have already good connection with Germany, especially Freiburg and Karlsruhe. And we have already good connection with them and exchanges with them. There is also this Nubias structure which exists. And we have also collaboration with Swiss, because Basel is less than 150 kilometers apart. So this is what we are, and I would like to end up with this advertisement. So if you want to go to any of these events, please feel free to ask Jérôme Mouterer, who will give you all the details about these events. And I thank you for your kind attention.